Hi, it's Robin. What do worms, adventure construction set, financial cookbook, cut and paste, Starflight, and chipwits all have in common? Anyone?
They're made in fourth.
Hello, this is Robin, and this is Paul.
Hello.
Also known as Mad Garden. If you can, try not to creak.
I'll try.
So my friend Paul is the programmer of Death Road to Canada. Now this is a Switch game, but it also exists for many other platforms, such as PC and...
Steam, PlayStation, Xbox, iOS, Android.
It's been actually a very successful game. Paul has worked for years on this awesome game, and I have several friends who really like it. So one very funny thing about Death Road to Canada is that a large part of it is written in a form of the language Forth, which Paul now calls Death Forth. Forth goes way back into the 70s, I believe, even the 60s. Yeah. And it's a really interesting language. And today we're going to be looking at it. Thanks to my friend David Yaud, he sent me this original copy of 64 Forth. Paul, what do you think about the name?
I think they missed the boat there. They could have called it 64th.
64th would have been way cooler, by Tom Zimmer.
But it's pretty cool.
And it came with this instruction manual. Oh, and I had that plugged in. And this cartridge. And in fact, that was brand new. I just opened it off camera. Whoops. And we've been playing with it this afternoon. So what we're going to do today is try 64 Forth. Forth is a language where the coder makes and names all their own programming commands, and everything is done on a stack. And of course, we're going to try and replicate the famous 10 print program. We're going to do it in Forth. So thanks to David Yaud for the cartridge. He also sent me this book, Starting Forth by Leo Brody, published by Forth Incorporated. We actually looked them up. They're still in business today. How about that? And this, the Australian Forth Symposium from May 1988, distributed by the Forth Interest Group in, that's weird, San Jose. That's the Australian Forth Symposium.
Notice how even the kangaroo is backwards.
It's true. Yep. So I booted up 64 Forth, 64th, 1.2 by TJ Zimmer. The first thing we're going to do is David Yaud sent in a version of 10 print that he made. So we're going to start with that one, and then we'll do one that Paul helped me with, and then I'm going to turn things over to Paul. We're going to actually even try to port that 10 print orthogonal, or orthogonal as I said originally. Okay, so let's just get right into it. And Paul, if you have any comments, so we're just going to make a program, actually a word. Isn't that what it's called?
Yeah, it's a word as opposed to a function. I guess because when you have a Forth program that's written cleanly, you can end up with what almost looks like an English sentence.
Okay. So :10 print, and then begin. Now you have to put white space between everything. Like I kept getting caught up not putting a space in front of the colon, for example. The other interesting thing, or one of many interesting things about Forth, is that is RPN, reverse Polish notation, also known as postfix notation, where you put the parameters, do we even call them parameters?
Yeah, parameters.
Sure. You put the parameters first and then the operator afterwards. Actually, that reminds me. Why don't we do something really simple just to show people what we're talking about there. 5. Oh no, I don't want a colon in front. That's her definition, right?
Yeah.
5, 3 plus. And this will give the answer of, oh, I did something wrong. Is it still on the stack?
Yeah.
Okay, so I pushed 5 on the stack, 3 on the stack, and then the plus operator would have pulled those two values, added them together, and placed the result back on the stack, right? Mm-hmm. So if I want to now print what's at the top of the stack?
Yeah.
Emit?
Not emit, but it will print what's at the top.
It will print, okay. And there's 8. That's what was I. So that actually pulled the 8 from the stack and printed it?
Yes.
Okay.
If you type .s, then it will display the stack.
It'll show the stack itself. And now the stack is empty. Yeah. And so if I went back up here, because this is using the Commodore Basic Editor, 5 and 3 again. And now if I just hit the stack here, I'll clear this first. It'll show there's an 8 on the stack. Right on. I'm just learning this. Paul has programmed a whole game in his own 4th that he made. So.
And I'm almost still sane.
Yes. I guess they'll decide that. Okay, so I'm going to continue this program. I see at. We've made a do loop here. That's going to count from, I believe, 32768 to 49151. And you were telling me automatically.
It basically pulls the index of the count and puts it on the stack. So
okay.
It's like a for loop, you could say.
Okay.
And it's like when you use for I equals. This is the same.
So just saying I is the same as taking whatever that count is currently and pushing it on the stack. Yeah. Okay.
The value is actually stored typically on the return stack instead of the data stack. Oh. So it pulls it from one position at the top of the return stack.
Okay. And then this C at symbol is essentially a C fetch. And so that gets
one character.
And it's treating it as sort of like a peak, isn't it?
That's exactly.
Yeah, it's like a peak. So what it's actually doing is value I is on the stack, which is going to start at 32768. It's a pretty crazy language, I guess, until you're used to it. 1.
That's an 8-bit peak.
Well, right, an 8-bit
C
peak.
is for char.
Character. Okay, yeah. And so that, in this case, is an unsigned character.
Yeah, I don't know what
although sometimes, yeah, we'll talk about that more later. Okay, 1 and 205. So it's done a peak. The value that was peaked from location 32768, and then the value 1, and then a logical AND between it. So we'll end up with just a 0 or 1. And then we're going to push a 205, which is the character of the slash in 10 print. That's right here. And then we're going to add them together. So we're going to have either 205 or 206. And then we want to emit that character. And finally...
why is this random? Can you explain that?
What's random about... Oh, yeah. What David's doing here is substituting, peaking the 4th, well, I'll call it kernel, but what we call the 4th machine code, the language binary. It's using that as essentially a random seeming. It's not random at all, but when you just boil it down to either a 0 or a 1, the low bit, effectively, it's
going to be pretty random.
It's 16,000 to us, fairly random numbers. And then he actually did an emit loop 0 and then until.
That wraps up the begin loop.
So the loop matches the do.
Yeah.
And then the 0 until matches up with the begin.
Right. 0 is never true, so it'll do an endless loop.
So there we go. That is David's 4th program. Does it work? Did I represent it correctly? We'll enter it into memory. And then I guess I can just clear the screen because all that junk. And here we go. And then to execute the word, you just type it in. And there we go. It is 10 print, running a lot faster than basic. If we hold down Control, it'll still slow down just like, because it's still, I think, going through the kernel print routine. Yeah, and it's as random as is actually needed for this kind of program. Okay, and then the only way out of these kind of infinite loops that we found is to hold down stop and hit restore, and it restarts 4th, but it doesn't actually erase what's in memory. I could still run temperate again. Okay, so that's David's version. Paul and I were working today and we thought it'd be fun to try and add SID randomness using the C64 SID chip.
Because the C64 fourth doesn't have a random function or a random word in it, so we needed to come up with some random. I guess they didn't expose the basic rand either.
Yeah. Okay, so what I'm going to do now is just show another one-line 10 print. Oh, by the way, that was a goal of David's, is to do it in one line, even though that's not really how you should do fourth, right?
Yeah, I mean, especially if you're going to be repeating or reusing parts of the code, then it should be factored into smaller words, like Lego bricks, which you can then assemble into more high-level words.
Okay, so here is somewhat, not necessarily improved, but we're going to use more of the built-in words in 64 fourth. We're redefining 10 print, and we're going to use this built-in one that is S init, which is sound init. Voice 3 is just telling the sound commands to use voice 3. That's the voice that we can actually read the random numbers out of that oscillator. All the other oscillators in the SID are not exposed. And we're going to set the noise waveform, and we're going to push a number on the stack, 65535, which is the maximum 16-bit value for maximum frequency. And there seems to be a convention in fourth that when you write a value, there's an exclamation mark or a bang afterwards.
Yeah, they call it store. And then the @ sign is fetch.
So if you see an exclamation mark, it's store. If you see an @ symbol, it's fetch. Okay, so we've set the maximum frequency, and that makes the SID produce random numbers at the maximum frequency. And then we're going to do S bang, and that is to supposedly write the SID values actually into the SID. For whatever reason, 64 fourth doesn't immediately do it. It kind of puts them into shadow registers and then copies them into the hardware. I don't really know why they did that, but they did. And then we're going to make another loop, begin, and we're going to read oscillator 3. Again, these are all built-in words, so that's fetching from oscillator 3. And we're also going to push the 1 on the stack again. Once again, do a logical AND. Add it to character 205, which is the slash. And then we're going to emit it, so that's just going to be the same. And then we just have to do an again. And the semicolon, yeah, whenever you define a word with a colon at the beginning, you have to end it with a semicolon at the end. And you need that white space between everyone. So this is exactly 80 characters. This is the maximum length possible. And now it says we redefine 10 print. Paul, what does that mean?
That means that we made another 10 print, and the previous 10 print still exists. So anything that calls 10 print before still calls the old 10 print. But now anything that is defined later, calling our new 10 print, will only call it. So it's a good way to override behaviors of existing words.
It's not doing anything really smart. It's just that the old ones are pointed to the old routine, isn't it? And now any new calls to 10 print are going to point to the new one.
Because when the word is looked up in the dictionary, it's just going to take the first one it finds. So we're just literally making a new one with the same name. That's it.
So all this stuff is stored. There's a dictionary, a fourth dictionary, which every time you make a new word definition, it sticks it in this dictionary, and you're gradually building a big, like almost like a new language or an extended language.
Pretty much every time you're writing a fourth program, you're making like a new language. It's not really a language to begin with. It's simply like a left to right parser of
there's hardly any language. Hardly any language there to start with, right? Yeah. It really encourages you to build your own.
You build a language that solves the problem that you're trying to solve.
Yeah, like 10 printing. Okay, so let's try and run this one. And does it work? There it goes. I don't know if that's faster or slower or what.
I wonder if the again is faster than the 0 until.
Yeah, right. Okay, that was one other change we made. Oh, now we can't bring it back, can we? Oh. Okay, so that is another version. Strangely, this version of fourth doesn't seem to really let you list a word the way you typed it in, because in fact, isn't the source code actually lost?
Yeah, the source code is only basically parsed and compiled into the resulting word. So unless you've stored the source somewhere, you won't be able to see it again. But there's a way to kind of decompile what's there.
Yeah, is that just the 10 print?
You have to actually source.
Oh, you have to do it first?
Source 10 print. Yeah, because this is a parsing word. Source actually parses the next token that follows off of the input. So it looks like you're doing not
RPN?
Yeah, not RPN, but it's really all it is just parsing ahead.
Okay, so that is like a decompiled version of what's in the dictionary.
That's the word definition.
The word definition in the dictionary. Yeah. So it's picking out where it does recognize existing words, then it prints the label name or the word name. But other places where we typed in, for example,
numbers,
the 205, the literal 205 is still there.
Yeah, but that's actually, it's not a high level fourth word. So what you're seeing there is literal 205 because it's a primitive. So it had to compile into the code a different type of reference to a code word, which was in this case literal, which pulls the value out of the code and puts it on the stack.
Wow. Okay, cool. Yeah, and even the branch, is that the actual number of bytes backwards?
Yeah, it just basically jumps back.
Yeah. So you can see how low level fourth really is. Like it's extremely low level.
It's pretty much an assembler.
Yeah.
And in fact, most fourths, like true fourths, especially from this age, have a built-in assembler word list that you can use to literally just assemble code right in your fourth code.
Yeah. Okay, so we've done these two versions. Paul wasn't happy with that.
I was furious.
Yeah. That wasn't good enough for Paul. He wanted to do that 10 print, I called it orthogonal 32-byte basic demo. So Paul wanted to try and write that in fourth, and instead bothering with this one line thing. I mean, one line is cool, but we thought it would be more informative to see an example of more real fourth code, a bit more of a practical use, but still a small example.
Yeah.
Yeah, okay. So I'm going to hand the keyboard over to Paul. We'll see how he does with this. I hope I can trust him with this.
Hi, it's Robin.
I don't do this with each syllable.
Yo, it's Robin. Some random name.
So what we're going to be doing is building up some words here, such as random init. This is an earlier version we had done just with pokes, essentially, storing values into these memory locations. And this is completely equivalent to that code I was showing you with the sinit and so on, just that we used a moment ago. So just so you know that these are available. Yeah, so what we're doing here is, so if we push 255 and then 54286 on the stack, then C exclamation mark is C store. So that just pokes a 255 into location 54286, which is the frequency register for, well, these are the pair of them are the frequency registers for voice 3. So that's just the same as when we stored that 65535 and set the frequency using those 64 fourth words. And same with putting 128 in location 54290. That is turning on the noise waveform in the SID. That's all that does. Just making you aware that if you just want to poke things, you totally can.
In fact, you could even do this.
Right on.
Boop.
There we go. Nice one.
So yeah, we initially tried to create a string buffer that held the orthogonal maze text, but this version of Force seems to hate Petsky, I guess.
Yeah.
It does everything in 7-bit ASCII range, and it filters out all our attempts to make a string using the original method. So do we want to...
Yeah. So go ahead and do
just
that.
show what happens.
Right.
QWER, and then Shift CB. So this is a dot print, I guess you could call it. It's a way to print a string out. It works either in compiled words or in the interpreter. So the results are not very mazy.
Yes. Yeah. So it should just print that Petsky back out again. Instead, it's stripped the high bit and it's a mess.
So we need to make our own buffer. So in order to make a buffer, we need to have a memory address to store it at. So we create a variable, maze string. So we're going to call it maze string. And by default, C64 fourth creates a variable with a 16-bit value in its data space. But we are not going to accept that. So we have to basically rewind it using the allot word, allot space in the dictionary for your data, for arrays or whatever it is you're doing. So we're rewinding it back to the start, and we're going to put our own crap in there.
So did the -2 allot took that -2 from the stack and did a rewind?
There's a thing called the dictionary pointer, I believe, in this fourth, and that's basically the pointer to where stuff is being compiled into the dictionary.
Yeah.
So now we're negative allocating that space.
Yeah, cool. You can just take it away.
Yeah. No restrictions in this language.
Yeah, so this language lets you do anything you want, including allocating negative
we're all adults
space.
here.
Yeah, we're all grown-ups.
So I have to type in the actual Petsky codes here. And these words, the C comma, is compiling into the dictionary space using that dictionary pointer. They're compiling a byte. So
it's compiling that literal byte right into memory. Okay. And again, we're doing this because, for whatever reason, 64 fourth strips the high bit of Petsky characters.
And that is that.
Okay.
So when you enter a variable, it will give you the address of the data pointer in the dictionary entry.
Okay. Okay, so we have made a string. And there it is. Okay. We made a string at location 4259. And then when you did the 6 type, you're telling it to type or print out 6 characters.
Right.
But it's still doing that same stripping thing when we try to use that. It's kind of funny that 64 fourth seems to do the stripping of the high bit, both as the data goes in and even as you're printing it out. Like,
you're gonna cut that little bit out?
Yeah, we can cut that.
We want to have a random generator that's not super weird, so we want to make a word for it so it's easier to understand what's going on.
Yeah.
So we will call it rand %, which will be a modulus-based rand calculation.
Yeah, and fourth lets you put weird stuff like %signs in the word names.
Yeah.
Almost anything goes.
So mod is an actual word here.
Those are all existing words. Swaps the 2 values that are currently on the stack.
Yes, because if we're going to do a modulus, we want to...
in this case, you want them in the opposite order.
Yeah.
Yeah, so we want 10 mod 7 value 3.
Yeah, so the value we're passing into the rand % word is going to be the value we want to modulate by.
Right.
To do the modulus of modulate.
Yeah, whatever.
We're modulating.
Modulating.
We're
the
modulating
modulus and
it's also it's sound, right? Modulation. Yeah.
Yes.
So we're doing that, and we have to swap them because they're in the wrong order once we get the random number.
And the mod command is built into 64 fourth, which is a plus. On the downside, well, we're going to find out the downside soon.
Mm-hmm. Spoilers.
Yeah, oops.
Now, the meat. Ortho, right?
Yeah, ortho. Hey, no! Ortho!
Not this time. Again. So yeah, we're going to get a random number between 0 and 5, and we're going to add it to the address of the maze variable, the maze string variable, which is where our maze string is stored. So now we can index into it and pull the data out.
These are all words that you have now added, like random init, you added random %, maze string. Those are all new features we've added to the language in a sense. Yeah. They're just equal with the built-in words, right? As far as fourth.
Yeah, these there are high-level words, and most of the fourth is actually written in the high-level words.
Okay.
And these are just more high-level words.
Yeah.
Those are the ones that when we run the decompile, we can see the actual names as opposed to the like literal value or other labeled versions, which are those would be code words, which you'd consider to be primitives that exist in the kernel of the fourth.
Okay, yeah. Okay, so we've now written the program. Is there anything else to explain, I guess?
So we're using, again, this is another fourth word used in control flow. Instead of 0 until, again, is essentially the official way of saying that. So
okay,
it might speed it up a little bit.
Yeah. Did we explain that maze string plus C?
Yeah, so I'm getting the index
Yeah.
of the byte, the random byte we want to pull out of this variable.
Yeah, okay.
And so this maze string gives us the address of where that data is stored. So I'm adding that random number from between 0 and 5 to the address.
Right. So in this case, with maze string, it's the address of the string, isn't it?
Yeah.
And we're adding up from between 0 to 5 with that random percent. That's returning 0 to 5. Or actually, it shouldn't say returning. It's pushing 0, 1, 2, 3, or 4, or 5.
You could say it's returning. Yeah.
On the stack. Then we're pushing the location of the maze string, and then we're adding them together.
Yeah.
Okay, yeah.
So it's essentially like indexing into a string, using like how you would with an array. This is just the arithmetic way of doing that.
This is the fourth way of doing it.
Yeah, or, the C way as well sometimes.
Yeah, that's true.
Crazy like that.
And then we did that peak. Oh, did that do something weird?
No, it's just that we redefined it and didn't need to. So
you did it twice. Okay.
So the forget word you can use to forget an existing word if you want to not keep redefining them as you keep editing them.
Yeah, because every time, Paul accidentally hit return on that twice, and that pushes to, when it does a redefinition, it doesn't delete.
It compiles
the
another version.
Yeah, it compiles it on top. Very interesting.
See if it worked.
Okay. Yay! Now, the orthogonal maze is pretty cool, but I do notice it's a bit slower.
It's slow, yeah.
It's a bit slower than those 10 prints we were doing. So what are you going to do about that?
We're going to fix it.
Okay.
We're going to make the maze itself a little tighter because we're going to have to trim a couple bytes from the output in order to get rid of the modulus. So it's going to be only a 4-byte maze.
Okay.
But it'll still look cool, I promise.
Yeah.
We need to make a new random word. And we will call this.
Okay. That's why you can use even an ampersand and
yeah.
That seems so wrong.
I know. But the thing is, you wouldn't be able to make this language without that because you don't have special identifiers or any of that stuff. So you have to just make it all yourself.
Yeah.
So you can call it whatever the crap you want.
Yeah.
Swap and. So with this, you will pass in the power of 2 minus 1 mask for anding.
Yeah. So what we're going to be doing now is, we're going to be anding the oscillator. Mod is a very slow, expensive operation. And the fast way of doing a mod is just using an and with any number of low bits set contiguously, like 1, 3, 7, 15, and so on. Okay, and you had to retype that. Oh yeah, because you just wanted to change it.
Yeah, so now we're adding the 3 rand and result, which will give us a number between 0 and 3.
Yeah.
To the address of the maze byte buffer again, adding it, then fetching it, and then emitting. And
so that's like a peak. Okay. Are you ready for it?
If you look at that in like Leet speak, it looks still like Ortha.
Ortha, yeah.
Seems we can't escape this.
Yes. Nice. And that is much, much faster. Yes. Well done, Paul. You have made a nice orthogonal maze.
You can hardly tell the difference without the bars either. The straight bars still looks pretty.
Yeah, it's still a nice looking maze. Yeah.
It might even be more mazy.
Yeah, in some ways this is more pleasing without those 2 bytes. Okay, we'll swap. I think we've covered everything we were talking about, Paul. We had a great time today, so I'm visiting Paul here. And, you might have noticed that I'm at a different table here. And so different environment. It was a lot of fun working with Paul on this today. And thank him a lot for his help. Do check out his games. Look up Death Road to Canada. He's got other Mad Garden games available.
Sort of. They're kind of like falling off of the App Store because it's been so long. But there's some things around if you look. Eggnog Plus and Chilaxian, I believe, is still available.
So I'll put a link in the description there. And if you Yeah. Oh, yeah. Flapthulu. Yeah. I'll put a link in the video description to Paul so that you can check out some of his games. He does excellent indie work on those other platforms. And Paul, you used to code the C64 when you were a kid.
Yeah.
You were telling me some stories about programming in BASIC and kind of hitting some of the limits there. But I'm kind of hoping that Paul's going to find a way and make a bit of a return to the 64. We shall see. We were talking about some ideas today, and who knows, it might happen.
Could happen.
Yeah.
We'll see.
We will see.
We will see, probably. I'll do it in C.
In C.
Yes.
So thanks again to David for doing that research about finding all those existing C64 titles. There'll be links in the video description to podcasts where the original authors talked about how they used Forth to make some of those games. Thanks also to David for sending this cartridge in and for helping inspire this. And it just so happened that I was going to be in Paul's neighborhood. I thought, perfect super team up. I don't know if I could call this a super team up. Yeah.
Nerd bump.
That was so awkward. Let's try, can we make it even more awkward? All right. Thanks to my patrons for their support. By the way, includes both Paul and David. Yeah. And thanks for watching. We'll talk to you next time.
See ya.
Bye-bye. Hey, stop right there. What's that supposed to mean? Can't you say anything else? Well, what else? Positive or negative? 0 or 1? True or false? On or off? You're a bit where's your program? Am I your program?